So this is the part 3 of this chapter. Okay, part 3 is called spanning set. Sets. Okay, let's start with the definition. Okay, so let's define the span. The span or linear closure. Okay, so the span or linear closure of an empty subset S of a vector space is the sets of all linear combinations of vectors from S. So we write the span of S, so square bracket, S inside square brackets, the span of S is equal to, okay, all the linear combinations of the vectors of S is equal to C1 S1 plus C2 S2 plus Cn Sn such that the C1s, okay, Cn element of R, and the S1 vector from the set S, element of big S, set S. Okay, quick note here. Okay, let me write it here. The span, okay, this is important. Okay, the span of the empty subset of a vector space is its trivial subspace. Okay, the span of the empty subset of a vector space is its trivial subspace. Okay, so let me continue. Number 2 here. Let's have a look at this lemma. Okay, okay, in a vector space the span of any subset is a subspace. Does it look familiar to you, the subspace we have done in the previous parts? We have seen that the subspaces are linear combinations of some structures. And here as well we say that the span is a linear combination of some structures, I mean, of some vectors. Therefore, can you see the link between a span, and a subspace? Yeah. We can just describe subspaces as being subsets. We can describe subspaces as being the span of some basic vectors. Okay, let me give you the lemma. In a vector space, the span of any subset is a subspace. Okay, so let me give you a note here. Note, the converse is not. Oh yeah, I think the converse also holds. So the span is a subspace, and the subspace is going to be a span, okay, of a certain number of vectors. Okay, let's say the converse of this lemma holds. The converse is also true. Any subspace is the span of subsets of some set. You see? I don't know if so far you are seeing the logic. We started with the vector space, and then we have seen subspaces being subsets of vector spaces, and those subspaces are made of spanning sets, are made of a certain number of vectors that when we take their linear combinations, we get the subspace. So we have this vector space being the bigger thing, and then followed by the subspace, and followed by the spanning set. Isn't that beautiful? And in the future, we will learn more about that spanning set, that set of elements that if we take their linear combinations, we will get the subspace. Okay. So I think I'm going to stop the lecture here, and in the next video we are going to show that the span of a set is a subspace. How to show that when we are given a set, okay, so the spanning set, if we span that set, we are going to get a subspace. Okay, see in the next video, in the tutorial.